Hello again. We were talking about general purpose inputs and outputs, in short, GPIO. And what we have covered the previous week was a gentle introduction to the subject and actually a gentle introduction to the GPIO circuit pad on our board, which you can see in the camera. And we've learned that there are 6 separate ports on the card. In other words, we have 6 of these separate circuitry for each port on our microprocessor and card. So this was the microprocessor, that box at the middle, and we've got 6 ports. And what we also said was you can connect any kind of digital or analog devices to the 8 pins of these 6 separate ports. Total 6 times 8, 48 pins. And we also said that we have already connected devices on this educational board. I mean, this is the microprocessor, that guy over here. So this guy over here, this one, sorry. This guy over here is the microprocessor. So the ports and the pads are all in this black box. However, this card for educational purposes has some additional connections, such as you've got the you got 2 switches connected to the pins of port F, PF0 and PF4. This being switch 1 connected to PF4. This being switch 2 connected to PF0, as you can see here. And also 3 pins of port F, PF1, PF2 and PF3 was connected to this RGB LED. This is an RGB LED. This is a digital LED. Digital LED means you can only send zeros and ones, guys. So digital LED means inputs are zeros or ones. It means you cannot send voltages in between. So you either send 0 volts, and in our system 1 is 3.3 volts. Well, you cannot send 1.5 volts. For example, you want to create low intensity, just you want to dim the light. You know, that's called dimmers. If you want to change the intensity of the light, you dim the light. So it doesn't work like dimmer. This is a digital LED. It is on or off. Okay, that's how we work on these. And we've learned how to manipulate the necessary control registers so that our ports will be ready to be used as an output port for PF1, PF2, PF3, so that we could use the LEDs. We have gone over the initialization procedure, the configuration procedure, how to change which registers, and we have learned how to change them in the assembly language. In the slides, you'll remember we have just covered these slides. So these were all separate blocks of code here, was to change a separate part of the microprocessor so that we complete the entire initialization procedure for the LEDs. Okay. And finally, when we are ready with the LEDs, we said that there's one more register, which is the data register, because in the end, what we are doing is there are 8 pins here. So these are the IO pins. So there are 8 pins here, 8 pins. So this is F0, F1. So if these are PF1, so let's say PF0 is here. If this is PF1, this is PF2, this is PF3, which are connected to the LEDs here, as you can see. We want to change the values. So how to change those values? We have the data register we set. Sorry, I'm going to get there. We have the data register we set. So if you try to change the value in this memory location, you would change the LEDs. So in other words, let's say I have a code piece like this. I'm going to write a code. So in the end, in the beginning, I have a directive like LEDs. So let me say LDS, let's say it's LDS. This is not 5. Silemedim ya. Dur bir saniye, onu silmek için discard bir daha yapıyorduk. So I say LEDs equal this value, guys, this value. I can name it any way I want. So in this example, it was named as this. data register, but I name it differently, just for fun. So what I say is, for example, I say LDR R0 equal to LED, which means at this line of code, this value will be written into R0. And for example, LDR R1, let's say 0E. 0E in binary is 0, 0, 0, 0, so many zeros, and 1, 1, 1, 0, because you know R1 is a 32-bit register. So these bits are 1, the rest is 0 if I do this. And finally, I do this str R0, sorry, str R1, this is R1, to where R0 shows. R0 is showing the LEDs. So if I write this value to these LEDs data, since this address or this address is pointing to the data register of port F, actually these values will be written to the pins of port F. So this will be written to PF0 if that pin is configured as an output pin. Actually, in the initialization process, we only configured these pins to be output pins, right? So the other ones won't be affected. So I'm going to be writing 1, 1, 1 to PF1, PF2, and PF3. So as you'll remember, these were the LEDs, which will make all these colors 1, 1, 1, and which would make the LED being bright with the color white. Because in an RGB LED, what happens is, in an RGB LED, let's say, if this is 1, these are zeros, you have red. If this is 0, this is 1, this is 0, you have green. And this is 0, this is 1, you have blue. But about the values in between, so if you have 1, 1, 0, which color can anybody guess? It's yellow. In LEDs, this is so. So this is 1, this is 0, this is 1. Which color can anybody guess?
Purple.
Purple, thank you very much. And about this 1, 1, which color? In Turkish, we use the word turquoise for that, but it has a name in English. It's called cyan. And if you make them 1, 1, 1, it is white. And actually, we are going to test this today. Okay? And also, there was one thing more. You could use this register because this address is mapped to this register. That is the register here. It's written here. So it's this register. But frankly, about this register, more than one address value is also mapped. So you can access the values of this register of port F using this address value, or you can use other address values to access a single pin. For example, this is to reach only the first pin, PF0. So you can use this address to reach only PF0. You can use this address to reach only PF1, or you can use this address to reach the pins all together. So actually more than one address is mapped to this control register. I hope this does not confuse you guys. This could be a case. I mean, more than one address could be mapped to a control register, so you can access it with different names. It is like, you remember, I've always made the analogy, the addresses are the hotel numbers, hotel room numbers written on the door. So imagine we have a room number, we have a hotel door, which has multiple room numbers. So if I say room 64, you go to that door. But if I say room 104, you also go to that door. A room having more than one room number, but nobody else has that room number. So if I say 64, no other room has that number. This room has multiple numbers, but no, those numbers cannot be used by other doors. Any questions? I hope not. I mean, any questions? Let me wait. Okay. So we are going to make, please.
Şey diyecektim. Hocam şimdi biz buraya bu adresin içerisine attığımız değeri mi göremedi ledler yanacak?
Good question. Your friend is asking, so will the LEDs will shine or not according to the values that we put in this address, which points to the port data register, port F data register, which is this register here? The answer is yes. We can generalize this yes such that, well, this port is, the purpose of this port is, there are 8 pins to use them as input and output, right? So whenever you want to use them as input or output, if they're outputs, we are going to write to data to provide the data outside as output. Or if they are input switches, we are going to read these pins. For both purposes, this is the register. So whether it's a LED, yes. It's a switch, also yes. So that's the data register, the data, the pins that you see at the pins. But before being able to use this, we have to make these initializations. So the answer is yes, but I try to give a more general answer as well. Okay?
Okay.
Okay. So guys, let's do this. I mean, let's make those LEDs on and off. How to do it? Well, we have the code. By the way, guys, this is a code I want you to download. I've told you this in the previous hour, but I'm going to remind you again. So this is our website, as you all know. You're going to click labs. You're going to go previous year's labs. You're going to go week 10. And at week 10, we have an assignment. And that assignment is about a project, and there's a solution. I'm going to talk about the assignment towards the end of this lesson. The solution for this code is provided, but I'll ask something about it as an assignment for Friday's office hour. Okay, we'll get there. Don't worry. Let's get back to our code. So this code is the solution that you'll download from here. This is the code. If you click this, you'll get this code. So as you can see, guys, I have GPIO port F data register here. And all the necessary data control registers of the port F, I already defined them. So in my code, I don't have to use these address values. I'm going to use these so that my code will be more easy to read. Okay. So I've created some global variables, which I don't care. For this particular example, I don't care. You'll need to understand these when you go home and study the example, but for now, just forget about them. So as you can see, guys, it does some bunch of things. Forget about them. Don't care about this part of the code as well for now. It calls this subroutine. This subroutine is called only once. It is called port F LED initialization. Simply, it is the initialization routine to prepare port F so that we'll be able to use the LEDs. It is the exact same initialization routine we've gone through in the previous hour in the slides. Remember this code and this code. It is the exact same code. So it is here. Port F LED. This is the subroutine for initializing the LEDs. It is called once in the beginning of the main function start. Yes. Not at the beginning, but towards the beginning. So you got it here. So what did it do? If you remember the previous hour, you remember what this was all about. We need to make necessary configurations for the LEDs to work. And it is doing those necessary configurations. I'm going to go over it a bit quickly because we've got other things to do as well, but I'm going to go over it. So I'm saving my code, I'm building my code, and I'm loading my code. When I press load, the new code will be downloaded to the card. Be careful, guys. This LED may go off. It went off because a new code is being downloaded to the card and the card is reset. When the card is reset, all the ports are reset, including port F. So when the port F is reset, the pins of port F which are connected to the LEDs are also reset and they become 0. And the LED went off. That's why it went off. Okay. Now I'm going to go inside the code. Okay. To do that, I'm going to press debug. And it's at the start of the code. So where is it? It is waiting at this line. So before this line to run. So it's somewhere around here because this is the beginning of my code start. I press F5 or I press this button here, which will jump. So this will jump until it sees a breakpoint. Do I have a breakpoint here? I'll put a breakpoint here, guys, so that I stop before I run the initialization. So quick recap on debugging as well. I jumped and it stopped there. So I want to go inside the subroutine. How did we do it? Remember, F10 was to step, F step on, F11 was to step in, F10 step over or on. This step, it's called step out, but in MATLAB it's called step in. So I'm going to step inside the subroutine. And when I press F11, yes, it will step inside the code. So just guys, I'm here. As you can see, it's here. So I've got a name here. So how do I know that this value was already defined in the EQ part? So what was it? It was this guy. So this value was this. So when compiler is reading the code, whenever the compiler sees this thing, it is actually thinking that it is that number. So if I run this code, this value will be written to R1. So is it really happening? Yes. In R1, as you can see, I have this value, which is exactly the EQ of this value. So yes, as promised, that value meant the same value for the compiler, and that value was written to R1. So R1 is now carrying the value of this address. This is an address value. Okay. I'm going to be doing an indexed operation and get the values of this register to R0. So what this line does is, I point to R1. R1 is pointing to this register. That's a control register on my pad. Not on my pad. This is not on the pad. This is on the microprocessor. So it is this pad is connected to here. So this is the microprocessor. The whole microprocessor is here. Somewhere here you have this control register. Okay. So I'm reading the values inside the control register. I'm pointing R1. So this LDR, what LDR does is go where R1 points, get the values inside that address, and write it to R0. So after this line, I'm pressing F10. At R0, I have the values inside where R1 points, this register. So in this register, I had all zeros. That's why in R0, I have all zeros now. Okay. Now I have R0. In R0, I have 0, 0, 0, let's say. I'm not going to go for all of them, but R0 is 32 bits, so many zeros in R0 and zeros. And I'm ORing with this value. So it's all zeros again. 0, 0, 0, 0 is this nibble. So the other nibble is 0, 0, 1, 0, because this is 2, right? This 2 here. So this is 0, 0, 0, 0. If you make them OR, this one will be 1, the others will be 0. So R0 will be all zeros and 20 in hexadecimals. And let's do it. If you do this, so R0 became the result of this. I'm writing str to R0, which means get the value inside R0 and write it to R1. So when I do this, actually, the memory address where R1 points, which is this register, inside it, now I've got this 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 1, 0, 0, 0, 0, 0 thing, which is hexadecimal 20. That's how I've written inside into this control register. That was the way we've done it. This is the way you change the control registers. Okay? Any questions? So guys, I'm going to ask you a question. We could observe the memory, right? Anytime we want. Let's try to observe this address. We'll be able to observe it? Yes. It's just like a memory address. As you can see, you're observing the memory. However, it is not the memory. Because this address is mapped to that register, actually the compiler, this interface, thinks that you are looking at part of the memory, but you know that this is mapped to that control register. Actually, you're seeing in this 4 hexadecimal bytes, you are seeing the ingredients of SysTick control register GPIO. So you can observe these control registers in the memory watch, just like you are watching the memory, although you guys know that they are not the memory, they are memory mapped control registers. Any questions? Oh, okay. Any questions? No. So why did we do this 20-0? Well, please, if you don't remember why we've done this, please go watch the previous hour again, because for this particular example, everything is written in the data sheets. What we're trying to do is, this pad is dead. It doesn't even get clock signal. What the first thing we do is, we are feeding the microprocessor's clock signal to this pad. And to be able to do this, we are changing the values inside this register. And if we change the values here, this one, if we make this 1, it will be feeding the port F with the clock. That's how we do it. Okay, so you remember it, I guess. Okay, that's what we've done. Since we're not going to use port E or D or C or B or A, we didn't touch the other ones. And remember, before writing to this, I've read the value and written it to R0. Remember, it was all zeros, right? This shows you that initially, there was no clock being fed to any of the ports. That's why when we reset the card, the lights went off immediately. Because when you reset it, everything is set to 0. The ports are set to 0. You don't even get clock signal to the ports. That's a reset procedure defined specifically for this card. That's why when you reset your device, everything is set to 0. And you don't even get even a clock to your ports. And if you don't even have clock, your LEDs cannot work, which are connected to the ports. Any other questions? Okay, I'll continue, guys. As you can see, I have the yellow triangle here, which means I am executing, I'm about to execute this line. If I have the blue line, that shows my cursor is here. So I can change the cursor, but it is still here. So I'm pressing F10. One cycle doing nothing, one cycle doing nothing. So I think port F is ready. Now I'm going to change analog mode selection register, which is my second step in the initialization procedure. And if you go to the necessary datasheet page, which is written here, so be careful. It's written here. No, not the page. So if you look for AMSEL in the data sheet, we've done this in the previous hours. That's why I'm not going to do it. You can read the values. So let's see what the default values are. So in R1, you have the value of this address. As you can see, it is here. And this value is again equal to the value defined here. So GPIO, so this value is being equal to this value. Okay, makes sense. Everything is clear. I'm going to get the value of control register and write it to R0. Let me write it. It's all zeros. By default, analog mode selection register were all zeros. I'm going to change it with this value because I want to make these bits 0, 0, 0, 0, which is bit clear, guys. Well, they're already zeros. So why am I doing this operation? Well, it is redundant, but I don't know if the initial value was this. I mean, because when I reset it, it's 0, but maybe before calling this function, somebody else changed those registers and they were not 0. I don't know that. I know this because I'm debugging it. While you're running in a big code, there is no guarantee that these are ones, these are zeros. So I clear R0's bits, it doesn't change, and write it back to R1, where R1 shows. So actually, we didn't have to do these lines, but we, nonetheless did it because we want to guarantee that there is no analog mode selected for these pins because we have already connected digital LEDs to it. So what I'm trying to say is, well, theoretically, when we read this procedure, it made sense. But it doesn't necessarily have to change anything. Maybe those pins were that way already. But this doesn't mean that you don't have to, you shouldn't do it because you don't know it. You don't know the initial value of the analog mode selection register. So you set those values to the one regardless of their previous values. Any questions? Guys, do this. Make sure you go over this, okay? This is an important procedure. I mean, being able to debug the code uh, fluently as this is an important skill. You need that skill. I mean, and don't think that I'm doing it very, very fluently. This is the least you should do. So as you can see, I've written that to the memory watch, and the values of that address is written here. So it is, as you can see, this is the least significant byte, the next one, and the most significant byte. So these are the values. So you know how to read a memory. Since these registers are 32 bits, although some bits are reserved, if you remember the data sheet, they are defined as 32 bits, remember? So remember these data sheets. So they are 32 bits, as you can see. Since they are 32 bits, all of the control registers are 32 bits. When I'm watching the memory, I'm checking all these 4 bytes because 32 bits correspond to 4 bytes. Good. Now, I'm going to do this example as well, and then I'm going to get to the code. This is GPIO port F control register. It has a purpose. It is changing so that you use this, not the alternative function. And in the data sheet, it said that if you're going to be using PF1, PF2, PF0, this time we didn't change the bits. For this particular one, we've changed the entire nibbles. So for port F1, we have changed nibble 1. If we start counting from nibble 0, nibble 0, nibble 1, sorry. So nibble 2, nibble 3 kind of. So let's see what are the values. So I'm getting the address value to R1. In R1, I have the address value. And because it was defined so in the EQ. As you can see, this guy, the same. Good. So I get the initial value to R0. At R0, they're all zeros because initially it was zeros. Nobody else changed it. And after reset, it was all zeroed out. So I'm going to be making them all zeros again. This is bit clear. So again, this is not changing anything because it says clear these bits and do not touch the others. Remember how bit clear worked. It worked on masks. So I'm clearing these bits. I'm not touching the other bits, but they're already all zeros. So I'm not changing anything again. Nonetheless, I do it. I've written it. So if you just look at that register memory value, if you look at that part of the memory, again, 0, 0, 0, 0. Okay. The important pins were, if you look at the data sheet, this, this nibble, PF1 being 0, PF2 and PF3. Because this is the least significant and this next and this is the most significant. So be careful, guys. The way it's written in the memory is a bit complicated because in the memory, first the least significant byte is written because of the little endian rule. Okay, so what I'm trying to say is, let's go over this, guys. This is important. So, guys, this is this control register mapped to this address. So each address occupied 8 bits. So that address is this guy, right? So if you look at the data sheet, it will show you a long data sheet, right? So 32 bits. Okay. I'm going to write them in nibbles. So the first nibble, the second nibble, 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 nibble. So I'll have 8 nibbles. 1, 2, 3, 4, 5, 6. So 1, 2, 3, 4, 5, 6, 7, and 8. So we've got bits in these. So 0, 0, 0, 0, işte 1, 1, 1, 1, 1, 1, 1, 1, 0, 0, just making up numbers, 1, 1, 1, 1, 1. Sorry, not 1. So these are the nibbles. So guys, if this is the control register mapped to this location, the first two nibbles will be mapped to that address. The next two nibbles will be mapped to the next address. D after C, D. So guys, this address is 40 million something something C. This address is, the next one is 40 million number D. E, F, it goes on like this. So actually, when I say this 32-bit control register is mapped to this address, I mean it starts from this address. The first byte is this address. The second byte, the third and fourth nibbles, are the next address. The fifth and sixth nibbles are the next address. So it is very similar to how memory is mapped. And this is 5 to F, which is this address and which is these four nibbles. Any questions? Okay, so let's make it clear here as well. So guys, this was the address. If you count, sum these numbers up, you remember this. This is another register, but this is the control register. So GPIO is this value, right? As you can see, which is, if you look at the data sheet, the summation of this guy and this guy, as you can see, 40 million FE 608, 40 million FE 608. So guys, if you say 40 million 608, it means that the first byte, this part is that address, 40 million FE 608. And the next address is 40 million F, I forgot to write E, I'm sorry, E, FE 609. The next address, 40 million FE 600 and A. Be careful, these are hexadecimal numbers. We don't have 10. 40 million FE 600 and B. Any questions about this control register being mapped to an address and it's corresponding to 4 different address values in the memory? Any questions? Good. Good. Okay, let me clear these, clear all drawings. Okay, now guys, after all these operations, we are ready. So I was here. I'm going to pass a bit quickly. So I just may do my F10s and F10, F10, F10. I'm doing the necessary initialization procedure that I've done previously. So it's done, it's done, it's done. So we are finished with the initialization. Now, if you want to write something to these LEDs, actually, if you write to port F1, 2, 3 using these addresses, we'll be able to. Let's try. Let's try using this address value and write it. So I'm going to be using this only pin address mode. It will, because this pin will make me change only one pin, which is PF1, which is connected to red. So I make F10 and I finish with the subroutine. Now I call another subroutine. Okay, let's see what does that subroutine do. I'm going inside the subroutine. I press F11 again. So I'm here, guys. What I'm doing first is I'm pushing the values R0 and R1 to the stack. Before I go out, I'm going to pop them out. The reason I do this is I'm going to be changing R1 and R0 inside. If the guy who called me, if that guy, the main function or another subroutine who called me, who called this subroutine SSR off, is using these R0 and R1, I don't want them to lose those values. So it's like saving R0 and R1. And when I'm finished, loading the initial values back. So nobody gets badly affected because I'll be using R0 and 1. So it is like this subroutine is a responsible subroutine. It is it's changing R0 and R1, but it is leaving R0 and R1 when it's finished the way it has found those registers. So bilinçli, responsible subroutine. So the first thing I do is I load PF1 to R1. What is PF1? Let's say what if this is this value because it was defined here, PF1. It was defined here like that. So I have R1 is a pointer now. It is pointing to the yellow triangles here. So R1 is pointing to that location. And that location is, yes, it is this location. That single bit is mapped to that address, sorry. If that single pin is mapped to that address, if I change this pin, because this address doesn't allow me to change any other bits, if I change the first bit starting from 0, I'll be changing PF1 because that's what it's for. So what I do is I load 0 to R0 and I load R0 to R1, which will make PF1 0. This subroutine is to make all the LEDs off. You may say the LEDs are already off, but that's also an initialization. That's a redundant operation, I know, but I'm making the LEDs off. Anyway, I'm doing it for PF2 and PF3. Could I have done it using this register all at once? Yes. Load 0 to where this register shows. You'll be loading 0 to all pins at the same time. You'd be doing the same thing. But I've done it this way. So the LEDs are off. Okay, now where the magic begins. I'm going into another red on register. This is red LED on. So save R0 and R1 again for the same purpose. Responsible subroutine. Guys, I'm making R1 point to PF1 and I'm loading this value to R0. When you load this value to R0, R0 becomes this value, this 2 in hexadecimals. 00002 in hexadecimals is in binary, as you can imagine, all zeros, 1 0, this bit being only 1. So if you look at here, that's the exact bit to be used by this mapping mode. So if I change this bit to 1, and if I can write this R0, it is R0 now, to where R1 points, I'll be changing that register. That register is the data register, and it will make that PF1 1. So when I execute this line, if I press 10, I'm expecting the LED on the device to be bright in the color of red. Are you ready? STR-R0R1, are you ready? I'm pressing F10. F10, and it's red. So that's how it happens, guys. Any questions?
Hocam bayağı bir önceye yönelik bir soru olacak ama karıştırıyorum da genelde. LDR sağdan sola doğru, SDR da soldan sağa doğru
Well, yeah,
yazma
the
işlemi
direction may
yapıyorsunuz.
confuse you, but LDR is to load to the scratch registers. Store is store the value of the registers to the memory or where memory points. So it is like think of registers are inside the microprocessor and memory and devices are outside. They are all inside. But so registers are inside. LDR is loading to inside. STR is storing to outside. Okay.
Okay.
Okay, so get used to it. The only way to get used to is to just do these codes hands-on. I know that you're doing it, guys, but as you do it, you get used to it. Okay. Now let's make another practice. Let's write a code, a simple code. Arkadaşlar, şehri mi durdurdum ben?
Evet hocam.
Çok güzel.
Evet
Evet
hocam.
hocam.
Nasıl becerdim ben o şeyi acaba? Şehir durdur tuşuna basarak düzeceğim şimdi. Çünkü debug'ı durdurmayı şehir durdur tuşuna basarak yapmaya çalıştım. Okay. Now I'm stopping the debug. Stopping the debug now. Just pressing here. I stop debug. I'm going to write a simple code. I mean, these were ready codes, but to make things simple for you. New subroutine. LEDs white. I'm going to make the LEDs white. All white. The LEDs are doing some color change right now. Don't care about it. That's the code you're going to go. So LEDs white subroutine. Routine makes the LEDs shine white. Simple, right? And it's going to be LEDs white. It will be a very simple subroutine, guys. I'm going to be doing this responsible coding again. So this guy. And this time I'm not going to be using this pin maps, but this data register to show you that it also works. Do I already have the constant definition for data register? I do. Yes, I'm going to use it. So I'll make R1 point to that register. I'm going to move R0 0 E, guys. This is all zeros in the most significant bits and 1110. And I'm going to store the value of R0 to R1. Anything wrong with the code? Would you like to say, because I could be doing mistakes. If you realize anything wrong with the code, please tell me. So this is pointing to that register. When I do this operation, R0 will be in hexadecimals, all zeros, E, and in binary it is zeros, 1110, guys. Since this is port F data register, this is PF1, PF2, PF3, I'll be writing once all registers all at once. Hope you are not making a mistake. Let's first save it. Let's first build it. Errors, no errors. So that's it. I'm going to be calling this function now. So instead of this, I'm going to be calling this. Okay. Okay, now I'm going to load the code, reset it. Okay, let's do it. Will we be able to do this? So I'm here. I just, it went inside it. I don't want to go inside initialization again. So I'm just going to jump to this code. So we'll be ready. Guys, we are ready. I'm going inside my newly written subroutine. So guys, R1 points to that data register. In R0, I have this value. Now guys, I'm writing the value inside R0 to R1. So if I execute this line of code, this instruction, I'm expecting the LED to be all white. Ready? White. So that's simple. Okay. So let's try the colors that we've spoke of. So remember the colors. So PF3 is green, PF2 is blue, PF1 is red. Let's try to get the color yellow. Yellow is, this is off and these are on, which is, so instead of 1110, 1010 I would need, which is, guys, A. So this becomes yellow now. Shine. Because, let me write it.
Hocam şey değiştirmediniz.
Hangisini?
Tamam hocam, ben şeyde bak başlattınız sandım, özür dilerim.
Ha, yok. Yeniden save etmen lazım falan diyorsun değil mi? Doğru söylüyorsun. Yapacağım. So this is PF1, PF3, this is green, this is red, and this is blue. Green plus red will be yellow. That's what we are talking about. Okay, let's see if it is working. Save, rebuild, one error. As you can see, I'm calling LEDs white, but there is no LEDs white subroutine anymore because I've changed its name as LEDs yellow. So save, build again, no errors. Load it to my card, stopped working. And I am just running my code. Vaktimiz dolmuş ya gençler. Neyse, hızlıca bitiriyoruz. Okay, I'm going to do step on and it's going to be yellow. Okay, any questions? I guess not. Now, guys, a good question would be how to obtain the colors in between. Because as you can see, it's making a nice show right now. It's creating the colors in between because there's already a code inside it to create it. But how come? I mean, we can only send zeros and ones to these registers. So how to create the color, for example, orange? We can create red. We can create yellow. How to create orange? Because I cannot send half to the digital channel. I only send one or zeros, right? Any ideas? How to create colors in between? Well, I love the kind of questions I ask and the answer is on the screen. With RGB LEDs, we create color by an illusion. The illusion is we turn red for a little while, we turn white for a little while. So actually, if you make, for example, this is the signal that we send to the red. For example, red, when red is 0, it is off, right? I send 1, okay? 0 and 1, 0 and 1, and 0 and 1, okay? Actually, when you send this signal, not only 1, you quickly change zeros and ones, what you observe is a darker red. Does this make sense to you? If I send to PF1, not always ones or zeros, like a signal like this. If I do it very fast, your eyes cannot see it. What your eyes can see is it's changing so fast, like thousands of times in a second. Your eyes cannot sample it. What you see is something between dark and red, which is darker red. Does it make sense?
Ben anladım hocam.
Okay. So in PF3, in PF2, I have blue, remember. I'm sending zeros. And in PF3, I have green. I'm sending green. All the way long. Which color will we seeing? I mean, when at this point, time point, it will be this one being 1, this one being 1, this one being 0. At this point, it's going to be yellow, right? At this point, this one is 0, this one is 0, this one is 1. At this point, you are seeing yellow. At this point, you are seeing green. Yellow, green, yellow, green. If you do this very fast, it's going to be a color between yellow and green. That's how you obtain the colors in between. And actually, the code that you download creates a rainbow of colors. I'm going to show that to you. Let's see, are you ready? So I just I'll find the camera. Nerede bu ya? Yes, are you ready? As you can see, it's creating different colors like the rainbow, like Melik Gökçek's rainbow you've seen in the streets of Ankara when you were a little child, because I was a young man of your age when I saw that terrible thing everywhere in the city. So it is, I call this Melik Gökçek's rainbow. Well, actually, this code creates Melik Gökçek's rainbow. So the assignment for Friday, it's a bit strange code, guys. Observe the code, try to understand how the code creates this rainbow. And if anybody cares to explain it to us on Friday, we'll see his or her explanation and presentation.